2M1207 is also a pre-main sequence star, but this is a brown dwarf. Now, brown dwarfs are those stars, as you know, that are called fail stars. Nuclear fusion never really stabilizes in the center of the star for them to drop onto the main sequence. So they come close to the main sequence, they never get to the main sequence. So they are very dim, very little mass. However, this particular one, this is actually the first exoplanet that was detected around a brown dwarf by the 2MASS all-skies infrared all-skies survey, and this is a composite illustration of the star, the brown dwarf star, and its planetary companion. The size here is to scale, but not the distance, because this exoplanet is orbiting this brown dwarf at a distance that is twice as far as the distance that Neptune is orbiting the Sun. Weiss 1049-5319 is actually a binary system consisting of 2 brown dwarfs. It wasn't too many years ago when brown dwarfs were still kind of theoretical, and now there are just thousands of them everywhere because we now have the technology to detect them. So this is a 2 brown dwarf system, and because of perturbations in the orbit, there are likely exoplanets there that have not yet been detected. This is a brown dwarf that was observed by the Chandra mission in a very early observation, and after 9.5 hours of observations for this brown dwarf, all of a sudden there was this huge X-ray flare that came from it. Now, this was the very first time that an emission from any wavelength whatsoever was seen being emitted from a brown dwarf. And all of this energy, remember, there's no nuclear fusion, any significant amount of fusion taking place in the core of a brown dwarf. So it is the energy being released is being produced by the release of gravitational potential energy as the star is still contracting. Gliese 229b is famous for being the very first undeniable detection of a brown dwarf, the very first one. On this graphic that we use all the time to show stellar evolution, down here at the bottom is that brown dwarf. It's located on here, though that brown dwarf never becomes a main sequence star. It just remains a brown dwarf forever. Up in this area are the protostars that would be the her big AEBE stars, the FU Auris and the T Tauris that are progressing towards main sequence stars. And if you plot these pre-main sequence stars on the HR diagram, you will see the general location, the her big objects, the FU Ori objects, and the T Tauri objects. Again, all depends upon their mass. They are very variable in their in the output of their radiation, and therefore their brightness and luminosity. So they do produce light curves, and they might look very similar here, but there are distinct differences between the output of light curves from these different objects. So you still need to know that. I kind of like this little exoplanet graph called the periodic table of exoplanets. Ignore the numbers because this was put out in 2011, and since then, of course, there have been hundreds of more exoplanets detected. So, but I'm showing this graphic for one reason. This is sort of like Goldilocks and the Three Bears. These stars are too hot and these stars are too cold, and you have to have just right conditions to have exoplanets that have the potential for habitability. And of course, the main reason we are interested not in solar system objects and in exoplanet objects is that we are looking for habitability. This is a graph of the separation in AUs of exoplanets from their parent star. and according to their mass, and they are plotted by the method that was used to detect them. And so you can see that radial velocity is a major way to detect exoplanets. And there are several that are detected by transit timing. Some of them, the ones way up here in the corner, by direct imaging. We are not going to talk about microlensing for the 2015 event. We're only interested in radial velocity, transit timing, and direct imaging methods. One class of exoplanets are the hot Jupiters, and hot Jupiters are obviously very, very hot. They're very massive, and the reason they're so hot, though, is that they are orbiting so close to their parent star, usually within 0.5 AUs. And because they are that massive and orbiting that close, they produce large oscillations in the orbital motions of the system, so they're most easily detected using radial velocity measurements. They also are thought to have migrated to their positions, that they're so close to the parent star because they migrated there, because there will not be enough material close to the star for something that massive to form. So they are thought to have formed much further out in the debris disk and then gravitated closer to the star. Another hot Jupiter is this. I understand there's a campaign underway to actually name exoplanets some, easily to remember, common, ordinary name instead of all these numbers, and that will be helpful. But HD 20945, 8b, is a hot Jupiter, and that particular one, it has a lot of firsts. It was the first detection of an exoplanet using the transit method. It was the first one that was detected using two different methods, and it was the first one that had an atmosphere detected, the very first one. But that's a sort of a caveat here when it says the first, because sometimes they will discover a planet and then decide it's not a planet, and then they might, after further observations, discover it really was a planet. Sometimes if you go back and look in a debris field using better technology, better image analysis software has been developed, they actually detect things that were actually there that they did not detect before. So that first can be taken with a grain of salt. This is another hot Jupiter transiting in front of a planet. This is a Chandra image. And this one, as this planet was transiting across the surface of this planet's star, there was a, as it blocked the light coming from the star, there was a 3 times greater decrease in the X-ray radiation coming from the star than there was in the optical, which means that the region being blocked by the planet itself is much smaller than the region being blocked by the X-rays, which gives an indication that there is an atmosphere there, and also the depth of the atmosphere around that planet. So this planet has a very large atmosphere. Spitzer actually did a global map of this exoplanet, which actually blocked out the thermal region of the surface of this exoplanet. And this exoplanet is tidally locked to its parent star, but the hottest spot is 30 degrees offset from the tidal locking point, which shows that there have to be, not only is there an atmosphere, but there are strong winds in that atmosphere that are distributing the heat around the surface of the exoplanet. Kepler-7 is an F or G spectral class main sequence star that's nearing the end of its main sequence stage and will soon transcend probably to the red giant stage. It has an exoplanet, Kepler-7b. The exoplanet is 1.5 times larger than Jupiter, but only 1/2 of its mass. And again, a surface map has been constructed. This was actually the first time that there was an inference of clouds on an exoplanet because of the distribution of the temperature around the surface of the planet.